Namaskar. Semiconductors is a critical and emerging technology, and India has been reacting to this need by announcing the Indian Semiconductor Mission, and subsequently, specifically for the development of microprocessors, which are the brain behind any digital system, which are the programmable entities of these digital systems. The Ministry of Electronic and Information Technology has announced the Digital India RISC-V derivative effort. Friends, RISC-V is an open source instruction set architecture, and there are more than 1,000 members in this RISC-V consortium developing customizable microprocessors. The need of the hour today is not just one general purpose microprocessor, but a family of microprocessors that can go on to very small embedded devices, to IoTs, to IIoTs, the industrial IoTs, to other medium scale embedded systems, laptops, desktops, mobile phones, all the way up to high end data servers and high end web servers, etc. So, there is a need for what we term as the domain specific architecture. Friends, I am very happy to present to you today yet another successful SHAKTI chip that was jointly developed with the Indian Space Research Organization, ISRO. The specific lab of ISRO that was involved was the ISRO Inertial Space Unit, the IISU, located at Thiruvananthapuram. This successful booting up of the silicon, which was completely conceived, manufactured, and the entire system developed in India, is yet another demonstration of Atmanirbharta in semiconductor manufacturing, specifically in the manufacturing of microprocessors. So, this is a complete Make in India effort. As you see, the specification and the funding was provided by the IISU Thiruvananthapuram in Kerala. The complete design and verification, including physical design, was done at IIT Madras. The ASIC tape out was done at Semiconductor Laboratory Chandigarh using 180 nanometers. Then the packaging of the same was done in Tata Advanced System at Pajjanahalli, Karnataka. This was a ball grid array packaging. The PCB motherboard was designed at IIT Madras. The fabrication of the PCB happened at PCB Power, Gujarat, and then the motherboard was assembled at Sirma, a company in Chennai. The entire software was designed at IIT Madras, and the system was successfully booted at IIT Madras. So, this is the Iris LV chip for you, which is a demonstration of the existence of a complete ecosystem from conceiving a project from its specification to actually realizing a system along with motherboard and booting, and all this happening within our country. These are all the stakeholders in this ecosystem has made this project extremely successful. I will take some more time to explain some of the technical features of this particular system on chip. So, this is a C-class variant, which is a 64-bit architecture. We have some amount of tightly coupled memory. We are working on a 180 nanometer. There is a 256 kilobyte tightly coupled memory, and with it's a fault tolerant memory. It has the error correction code. The ECC is implemented here. Then it has lot of peripherals, including PWMs, UARTs, SSPIs, CSPIs. It has GP timer, general purpose timer, plus GPIOs, and then it also has a external memory plus all the standard debugger interface. So, as far as the chip is concerned, the number of peripherals and external interfaces are equal to what we see in typically commercial chips used for typical applications outside. So, the chip is an aerospace quality chip, and we are very confident that this is a good quality chip where people can start developing and start experimenting and also start making prototypes. As in other commercially available chips, this has multiple boot modes. You can boot it through a debug mode, you can boot it through an external memory booting. We also have the SPI flash RAM booting and also the UART booting, and all these bootings are working successfully. Now, I will go into the specific of the microprocessor. The C class is a 5-stage 64-bit in-order core. The microprocessor internally has a 16 kilobyte instruction cache and a 16 kilobyte data cache, which is 4-way set associative. And it has a pretty large set of RISC-V instructions and a programmable clock frequency which can go all the way from 120 megahertz to 4 megahertz. It also has the standard Axie4 Lite interface and a JTAG based debugger support. So, this is the package chip that you see here with a ball grid array. We also developed this evaluation board at IIT Madras. This evaluation board actually has brought out all the pins so that any development, any verification can happen here. It also has a concept of what we call as pin mux, using which multiple different peripherals can be attached to the same external interface by programming this pin mux. So, the evaluation board has a system clock that is programmable using I2C, and as I told, all the pins are exposed, so you can do major developments here. And then the PinMux support ensures that this is Arduino compatible. Many of the Arduino compatible boards can be actually connected and many projects can be done. So, this evaluation board was funded by the Ministry of Electronics and Information Technology, Government of India, under the DIRVI funding. Now, we will just show the booting of the system, the hello world, and also some very interesting demonstrations. I am very thankful to both ISRO and Semiconductor Laboratory Chandigarh. I am thankful to the chairman ISRO, Dr. Narayanan, and Sri Padma Kumar, who is the director of IISU, for enabling this partnership, wherein lot of inputs had come from ISRO to make this aerospace quality, and I am very happy to note that ISRO will be using this in many of their coming projects. I am also thankful to Sri Kamaljeet Singh, Director General of SEL, Chandigarh. SEL has been of a great support to the SHAKTI project. This is a third successful chip that has come out of them. The REMO in 2018, followed by the Maushik in 2020 and the Iris LV now in 2025. I am very confident that we can work together to make many more wonderful chips for our country. Friends, what makes us very happy today is that the entire ecosystem for developing a semiconductor chip, right from its idea specification to the final system or motherboard, exists in our country, and we have demonstrated it, and this is of commercial quality, and this Atmanirbharta makes us very, very happy. We have been talking to multiple agencies regarding usage of SHAKTI, specifically in some of our very big programs of our country, including the ISRO. Another point, IIT Madras has the ISRO cell, which has been there for quite some time, and we had been having a lot of collaborations with multiple laboratories of ISRO. At that point of time, the IISU approached and asked us that if we could make a controller, specifically a microprocessor that is programmable and do many of those activities. And that is how we started this interaction. And when we evaluated SHAKTI, we found that it can suit many of their needs, and then that's how we came out first with an FPGA prototype, and then we were convinced about the functionalities, and then we went ahead and make a chip out of it. The SHAKTI microprocessor program has been conceived basically to bring in Atmanirbharta in microprocessor design, so that our own startups can make different domain specific architectures, our own agencies can make certain customized processors that will suit their specific needs. Today, a general purpose processor is not the one that is going to be of major use, in the sense that every domain has their own requirement, their own set of peripheral interfaces, their different needs. For example, how many peripherals I connect to a particular system is extremely domain dependent. So, one of the most leading topics today is domain specific architecture, and keeping this in mind, the RISC-V architecture has been evolved, and what we have done is yet another chip in the family of SHAKTI, in the family of RISC-V processors in our country, that can suit a domain like today space. So, we have developed an aerospace quality chip. So, the challenges for any microprocessor development is, of course, that we need good design engineers, because the chip, even though we are making a in-code processor chip, they have multiple clock domains, we have multiple set of peripherals, the verification need to be done, and all these things we achieved in an institution. Commercial quality tape out was done, and that to bring it to that commercial quality is what is one of the first challenges. The second challenge was availability of packaging here inside the country. We wanted to do it everything within the country. So far we had accessible packages, which we call it as QFN, which will be the pins will be on the edge of the chip. But this time we have the ball grid array, which is on the bottom of the chip. The pins can be taken out, and thanks to the Tata facility that had come up in Karnataka, where we were able to get this chip packaged there, and that was one challenge. And other things were the PCB design and manufacturing of the PCB, then assembling, and all these things being done inside the country. And once assembled, the fully assembled board came, with a matter of a couple of hours, we were able to bring the chip up, and that is also a very that gave us sort of confidence in making this type of complex chips in the country. The main issue here is that there are, as I explained in the presentation, there are 5 major steps. One is the design, the physical design, then the manufacturing, then the packaging, making of the board, assembly of the board, and then of course software. What we have demonstrated is all of this is done within our shows. So this essentially gives confidence that we have the complete ecosystem available in the country. What many people would say that we have still worked on 180 nanometer, we've got a 120 megahertz chip. But the point is that as we have done the design, so if the new fabs come, which we are anticipating in the near future, where we are looking at a 28 nanometer and probably much lesser also. As they come, it is only a matter of us changing the physical design kit and basically taking to that fab. The entire process can still follow. The process exists, the experience, people exist. We have also demonstrated students who have participated, multiple students have participated, multiple agencies have collaborated. So we have this ecosystem and the willingness to do something together completely inside India. And that is what we are actually focusing in this particular demonstration. And of course, this is an aerospace quality chip, and I am sure it is going to be, it will test the commercial requirements successfully.